Okay, our next paper is an analytical study of a cryogenic thermal control coating.
Right. So thank you for the introduction. My name is Jared Wilhite, and I'll be presenting with my friend and colleague Justin Elkert. And we're both in the Thermal Systems and Transport Processes branch here at NASA Glenn. And today we'll be presenting our analytical study of a cryogenic thermal control coating. First, we'll start with a brief introduction for the project, for which we both developed two different thermal models to thoroughly investigate the solar white coating. First, I'll go over the deep space solar simulator thermal vacuum setup, which I modeled, and I'll go over my results and findings for that. And Justin will immediately follow that with his lunar surface analysis of the solar white coating. And then we'll finish with conclusions. So cryogenic thermal control coatings are often used in spacecraft applications, and they're used to provide thermal control of the spacecraft. And they do this by, at the bottom shows the sun spectral radiance over a given wavelength. You can see that it becomes significant, starts to become significant at about 0.2 microns, about 10 microns. And the objective of the project that we're presenting today is to develop a cryogenic thermal control coating that can maintain temperatures for cryogenic propellant storage in deep space. And in order to do that, it's important for the coating to reflect most of the sun's irradiance while still allowing long wave emittance. And current thermal control coatings are limited because they absorb significant UV and long wave infrared. So in a recent NIAC study, an enhanced cryogenic thermal control coating called solar white was developed and tested. And there were many different materials that they looked into as potential solar white materials. Ultimately, yttrium oxide was selected. And because of its ability to reflect UV above 0.235 microns through infrared up to 8 microns, so that basically covers the entire wavelength band that you saw in the previous plot. Yttrium oxide also is lightweight, hydrophobic, and chemically stable, which is exactly what we're looking for this kind of application. So the picture here shows solar white coating, which is made up of a thick scattering layer of yttrium oxide on a thin silver reflector. And it shows the scattering layer is able to reflect the UV and visible radiation, and also most of the near to mid infrared, while the far IR, that's reflected by the thin silver reflector. And then the long wave radiation, the scattering material basically emits and radiates that energy, and that provides the cooling. And the combination of this scattering layer and thin silver reflector can theoretically reflect almost 100% of the sun's energy when used in deep space. And this will allow for cryogenic temperatures to be reached in deep space applications. Now for the deep space solar simulator. So DS cubed for short. This facility is located at NASA Glenn. And this is a picture of it on the right. So most of it is the thermal vacuum chamber, which simulates deep space conditions by establishing high vacuum of 10 to the minus 6 to 10 to the minus 7 torr. And it also establishes a cryogenic thermal background using the cold head adapter, which is shown here. And that drives the temperatures down to about 12 Kelvin. As far as the apparatus, there's xenon lamp solar simulator, which is used, and that's a big part of the model, which I'll discuss later. We have silicon diodes, which we use to measure temperatures of the sample as well as the simulator environment and other components. And we also determine the energy input at the sample. And for the solar white sample, we analyzed two different samples, so spray-on coating and a tile. So the spray-on coating, that basically was where the yttria powder was sprayed onto a small aluminum cylinder, as shown here. And the rigid tile samples like one shown here. Those were created by compressing and sintering yttrium oxide. Both samples were 1 inch in diameter. This ground sample was 3/8 inches thick. I believe the tile was 1/2 inch thick. Excuse me. So now I'll go into the DS cubed model that I developed. So I used Thermal Desktop to develop this model, and this is a screenshot of it. Starting with these are arguably the 3 most important components in the model. So you have the solar lamp, which is just a thin single node surface, and that transmits light energy through this 1/2 inch, well, 1 inch viewport through the silica lens downstream to the sample, and that's how the sample receives the light, light intensity. And yes, so that transmits light energy through the silica lens downstream to the sample. And these other components are cold head adapter, as I mentioned before. That's held at a boundary condition of 12.5 Kelvin with the cold Kevlar strings. And then you have the sample holder, which holds that apparatus together. And also the aperture, which goes over the viewport, and then the lens cover, which holds the silica lens and other parts in place. So this slide basically summarizes all of the parameters that were used in the basically setting up the DS cubed model. So starting with the solar lamp, as I mentioned, a single node thin surface. I used a normal optical property so that all rays were shot from the lamp surface downstream through the lens down to the sample. And I also disabled the conductance capacitance tabs so that there were no thermal effects from the solar lamp surface besides outputting rad Ks as heating rates, which that's an important feature of the solar lamp. And it emitted light intensity from 150 to 170 milliwatts per square centimeter. This was the same range that was used in the test for the DS cubed facility. The unfiltered xenon lamp, this aligns very well with the it aligns much better with the solar irradiance than a tungsten lamp. And the model that I developed, it runs 2 different cases. So light on, which includes the solar lamp, light off, which does not. And two different radiation analysis groups had to be created for the light on case. One that included the solar lamp and everything that was exposed to the solar radiance. And then the other radiation analysis group that included all of the components except for the solar lamp. And so light off, we only needed 1 group because the lamp wasn't included. And then for other parameters, 300,000 rays per node was used. Solar versus infrared that was used in setting up the solar lamp. So solar was selected in the rad group that included the lamp. Infrared was in the one that did not. And then wavelength dependent properties, we went from 0 to 25 microns, mainly because that was all the data that we had for the sample as far as optical properties. And mostly steady state was run, but there's also one transient analysis that I'll discuss later on. Okay, so now I'm going to start with the light off case because this is the most straightforward one. So this included, as the name implies, 0 lamp output and simulates an ambient emissive environment in which one inner wall of the chamber was set to ambient temperature. This case was run to ensure that no infrared reaches the sample downstream. And these results show that the silica lens was effective in preventing infrared from reaching the sample because that reaches the highest temperature with the light off of 23 Kelvin, and the sample remained around, it remained at 16 Kelvin. So the light off case showed us this. And then the light on case, as the name implies, the lamp output was set to the maximum of 170 milliwatts per square centimeter. And the sample was shown to reach 102 Kelvin with the lamp turned on. So these results were very similar to the sample temperatures that were measured in the DS-Cube test. And this is mostly visible light that the sample is seeing, and it's absorbing about 1 to 2% of that light. So that's where the increase in temperature comes from. But you can see that we're still very low temperature of 102 Kelvin. So transient analysis, this is supposed to, okay, there we go. So this is just a video of the transient analysis. You can see that the sample starts to heat up after the lamp is turned off. And what this is showing is this is after the chill down happens and the lamp is turned on. So this is looking at a spray-on sample case where we spray coated a 7075 aluminum disc. And you'll see that the trends are not exactly a match, but they are similar between the test and the model results. So that's what we wanted to see. And that could be because of slight difference between the specific heat data or some other discrepancy that we had. But they both approach an asymptotic maximum temperature, which is a good sign. And lastly, the additional analysis that I wanted to discuss, this was conducted to determine the percent of the solar lamp power that was absorbed by the sample. This was done using solar intensity, different solar intensity measurements, and .85, and plotting for different solar intensity values, 150, 160, 170. So the model setup here involved the same conditions as you saw for the light on case. All that was done, so basically just give a quick example. If we have a solar intensity input of, let's say, 150 milliwatts per square centimeter, and the sample temperature is about 90 Kelvin, the sample shows us the sample is absorbing about 1% of that solar flux input. And the results shown here were verified by calculations that were obtained in a previous Excel analysis. So in summary, the light off, that showed us that the silicon lens was effective in preventing IR from reaching the sample. The light on case was a conservative one because it assumed solar intensity of 170 milliwatts per square centimeter. So that's higher than the actual solar flux. And even with that, the sample was still able to maintain relatively low temperatures. Transient analysis that further verified the results because it was in alignment with what the test results showed. And the additional analysis that showed the effect of solar intensity on the sample temperature, and that the coating can reach about 90 Kelvin for lower solar intensity values. And in the near future, solar white will undergo further testing on the space station, where it will be applied to coupons used by ULA for testing. And now Justin will discuss his lunar surface analysis.
Yeah, I just want to do a time check. We got about 5 minutes left, so.
Oh, okay. I'm sorry.
We'll try to make it quick. Thanks, Jared. Thanks for tuning in, everybody. My name's Justin, and actually, so I was told about this project. They were working with Bob Youngquist, and he had come up with a geometry like what you see in the left there. It's kind of like there's a shield and there's like a tank kind of like sitting in there. There's nothing over the top. I mean, you could put maybe a radiator or something over it, something to think about. So more or less, we took a really simple approach. Like I think most people in this room know that modeling a cryogenic vessel can be, well, you can make it really complex. You can do kind of more of a simple approach. But I took the simplest possible approach because we just wanted to get a handle on how this coating works compared to other coatings, and also get a handle on lunar surface modeling. I don't know if anyone took that short course, so that all those principles were applied in this model. So that was, I think, a good way to go. You can model the ground plane. You can actually get those sort of corrections from the shadow and things like that, which is useful for getting a more accurate result. So just the most simple way to do this is to assume you have a solid LOX node, which it's not really possible. So we have a 400 kilogram diffusion node with the properties of LOX at saturation. So you're going to see it go to some warmer temperatures. It doesn't make sense, but it's good for sort of a qualitative comparison. And all we did here was we took either AZ93, which is more of a standard sort of reflective coating, compared it to this yttrium oxide stuff, at least how it's laboratory measurements. So I guess maybe a spray coating might be slightly different. And well, another drawback to mention is we only had data from 0 to 25 microns. So I kind of assumed out, because some of the energy is out beyond 25 microns. So we assumed that it had a greater emissivity sort of further out, maybe around I think the cutoff was 500 microns for this model. So that's about it for this slide. Next slide there. So on the left, you can kind of see the ground plane. It's not to scale. It sort of looks like I don't know, Death Star or whatever. But it's pretty much the moon, and you can see the ground plane. It's not to scale, but you can actually see it there, and you can see the path it takes as it goes around. I labeled in the graph there the lunar day and night. And you can see the LOX node temperature, and this hypothetical node gets up to around 335-ish. Something to keep in mind there. And just for this constant properties case, for AZ93, the solar absorptivity is listed there, 0.17, and the emissivity is 0.92. And there's some orbital details there. So next slide. So this is kind of an interesting slide. You can get a handle for the AZ93 case, at least. We have limited time in slides, so I don't have all the cases listed, but for this one, it's illustrative. You can see due to sort of the weird shape that there's a dip in the outer shield. And these are all heat fluxes, so you're just seeing what the relevant heat fluxes are. Notice that the solar's less than the IR. There's a lot of IR exchange happening. Some of it sort of cancels out, and then what doesn't, raising the temperature and the sensible heat there. And you can see that's sort of solar, because as the ground warms up and as the shield warms up, they both start emitting more. Next slide. So now let's look at this optical coating, yttrium oxide. We took a semi-gray sort of constant properties. We assumed it was, so we have two models, one with constant properties, one with wavelength dependent. We'll look at the constant properties first. Solar absorptivity 0.01, so it's pretty low, and emissivity 0.8. We don't actually have that data, but it's probably a pretty good estimate. And just on the right, you can see I've just plotted sort of the like on a log chart what the solar energy is, maybe at 5800 K compared to just a room temperature 300, and you can see sort of where the peak wavelengths are. So you can see in the solar region around like 3 microns, it's pretty constant around 0.01 if you look at the actual chart. By the way, since I go out to 500, I assume it jumps up at 25 to 0.8 and just is constant 0.8 out to 500. I don't show that on the chart because if I did, you wouldn't be able to see anything. And I have some of the wavelength bands listed there. I also, somebody else suggested maybe I should use more bands. So I counted like 0, 2, 4, 6, all the way up to 25 in another chart. So let's keep moving here. So you can see here when you run this fancy sort of yttrium oxide coating, you get a much lower temperature, maybe over 100 degrees less, 100 degrees Kelvin. And I also listed some of the heat fluxes there. It's kind of interesting to see they're much lower, as you would expect. Next slide. And then when you compare the equator to maybe this one, like a more closer to the pole, you even get much lower temperatures. So that's suggesting that these passive cryogenic missions, they're really latitude dependent as well. So your spacecraft geometry, your latitude, and as well as your what solar coating you're using, and other factors too. Like we didn't look at MLI in these models. So there's a lot of important factors, and these are a few of them that we're pointing out here. So let's go to the next slide then. So comparing, this is kind of interesting. If you do a wavelength dependent model, you're probably going to get more accurate results. Depending on the complexity of your model, it could take a really long time to run. So you got to be careful with that, because you have to run RAD-Ks now for every wavelength band, and that's why it takes so much longer. But you can get more accurate results. You can see here it makes a bit of a difference. Probably because I'm just assuming IR is 0.8 there, but now it's actually integrating over that part where it's increasing to 0.8. Okay, next slide. And then just comparing, so on the left, that's actually 6 bands. So there's a typo. I just counted 0, 5, 10, 15, up to 25. And then the other one, 0, 2, 4, 6, blah, blah, blah. And they turned out roughly the same, which is, you might kind of expect that, because over those bands, it's relatively constant. I think there's a part where it kind of like swoops, but those two regions sort of cancel themselves out, if that makes sense. So it ends up being more of a similar result. And next slide. Oh, that was it. Okay. So that's all I had. Just a simple model, and we're just taking a look at doing a comparison. We looked at a bunch of different geometries and stuff, so you can play around with this, and I think it's a good idea as a start. And that's all I had.
Yep, that's all for our presentation, and these are acknowledgements, and we're open to any questions anyone has, if we have time.